Okay, so we're going to talk about Missouri theory. I mean molecular orbital theory, but it has the same abbreviation. See, that was a funny joke, right? Try to keep it light at the beginning of my videos. Oh, there it is. Okay. This is molecular orbital theory. This is going to be a 9798 reading guide. I really didn't talk about this at all last year because I hadn't seen it on an AP exam ever. But they put in a little thing about molecular orbital theory on the new curriculum, so I thought, you know, I should probably at least touch on it. And that's really all we're going to do is just briefly talk about it, okay? So the idea here, and if you look at your 9798 reading guide, which, where did I put that so I can look at it? I gave you a lot of help on this one as far as the additional questions related to the reading. Instead of giving you questions, I kind of just gave you this whole long monster, several paragraphs about my summary of molecular orbital theory. So I don't know if this is easier or harder than just looking in the book, but I'm trying to kind of direct you to the places where you really need to focus on this because you don't need to, I mean, really in the book it gives a pretty brief overview as well, okay? But the basic idea of molecular orbital theory, this is probably a better bonding theory than the Lewis bonding theory that you have learned for the last 2 years. So why do we learn the Lewis bonding theory? Because large chunks of it work just fine. There's just certain problems.
Service, contact the main office, please. Sarah Service.
There are certain problems with the Lewis structure bonding theory, or the valence orbital bonding theory, whatever you want to call it, that come up. So one of the big ones is the Lewis bonding theory doesn't do anything at all to predict how a molecule absorbs or releases light. In the labs that we have done where things have absorbed or released light, we've kept it really simple by using, like with copper nitrate, copper chloride, those sorts of things. When you burn the chemicals in the flames, we usually use nitrates. Lots of announcements today. We usually use nitrates and chlorides because those don't give off any color. They don't give off light in the visible spectrum, right? So then you're just looking at the color of the copper. You're just looking at the color of the lithium or the sodium or whatever it is, okay? But there are certain molecules that as molecules they absorb or release certain types of light, okay? A lot of organic molecules are this way. A lot of the pigments that are in your clothing, that sort of thing, that's not just an atom that's absorbing or reflecting certain wavelengths of light, certain frequencies of light. That's an actual compound that's doing it, okay? And the Lewis bonding theory can't explain that at all, okay? So molecular orbital theory does a much better job of explaining how a molecule would absorb or radiate light. Okay, so that's one big thing. Another big thing is there are certain aspects of magnetism of molecules that can't be explained by the Lewis bonding theory either. Okay, so that's why two of the reasons why we need a better bonding theory, and the better bonding theory is molecular orbital. And if you go any further in chemistry in college, you'll probably learn more about this. But the basic idea here is this is really based a lot more on quantum mechanics, all right, which already you can tell it's going to be a lot more mathematical and a lot more abstract and that sort of thing. But we need to kind of understand how waves work, right? Now, those of you who have taken physics, you know about destructive and constructive interference, right? Have any of you in here taken physics? Okay. Did you talk about that? Constructive, like the constructive, destructive interference with a wave, or when two waves come together? Okay, all right. So you haven't, I guess. Yeah, all right. So you may not have a lot of experience with this yet, but basically the idea is with constructive interference, you get two waves that are kind of coming towards each other, okay? So these waves, if they combine when they're coming towards each other, if they combine in a constructive way, that what you end up with is this really big wave, okay? And I could show this better if I had an animation of it. But then there's another possibility called destructive interference, where you've got the two waves coming towards each other, and they might actually just kind of cancel each other out, and so then you end up with nothing, okay? So those are kind of your two possibilities. You can maybe think about this in terms of like a slinky, right? You've got a really long, stretched out slinky, and you've got two people making different waves on either end of it. You could end up, if they get in sync with one another, you end up with these really big waves in the middle of the slinky. Or if they're out of sync with one another, then the middle of the slinky actually might end up being perfectly still, okay? So that's constructive versus destructive interference. You can also experience this in certain places, like with acoustics, with sound waves. You can get this same principle. So a lot of times, sound, halls that are going to be, where concerts are going to be given and stuff like that, they build them in a certain way so that when the sound waves bounce off into the audience, they constructively interfere, and so you can actually hear very well. So when they talk about the acoustics of a place being good, it has to do with that constructive interference. And in the same way, like you can find dead spots in a lot of large halls where there's destructive interference and you can't hear anything. It's like all of a sudden someone just turned off the sound completely, okay? So it's just kind of, it's interesting how that works. But this is related to waves because quantum mechanics uses Schrodinger's wave function to solve for these orbitals, okay? And so the idea is when you have two orbitals bonding, because these are wave functions, you could end up with two orbitals that either constructively interfere with one another or they destructively interfere, okay? So constructive interference is kind of like the bonding orbitals in molecular orbital theory. Destructive interference is kind of like the anti-bonding orbitals, okay? And so that's, I don't know if that helps or makes things more confusing. But the idea here is if you've got hydrogen and you've got these two atomic orbitals here, okay, then what you could end up with is those two atomic orbitals sort of constructively combined. Then you've got your nuclei in the center, and most of the electron density is here in between the two nuclei. That's going to favor the formation of a bond, okay? Because the electrons are here, they're attracted to each of the, that's a horrible, horrible drawing if it doesn't mean anything. But the electrons that are in here in the middle are attracted to the protons on either side, and then you end up with something that forms a bond, okay? The other possibility here when these two orbitals come together is that they would anti-bond, they would have this destructive interference, and most of your electron density would end up over here and over here on the outside of the nuclei, and that's not going to form a bond, okay, because that's energetically not favorable. So those are your two possibilities there, okay? So basically, what molecular orbital theory does, okay, this is basically just talking about what I just said. Let me move on here. And there's the destructive interference. So what you basically do in molecular orbital theory is you take the orbital diagrams that we have learned, okay, and the orbital diagram for hydrogen is just this, right? And then you take the other orbital diagram and you put them on the two sides, right? And then you think about the bonding orbital that could form and the anti-bonding orbital that could form. And now remember, we talked about this the other day. When a bond forms between two things, the potential energy lowers, right? Remember talking about that? Because it's a more stable arrangement. So for this bonding orbital, this has a lower potential energy than the two atoms had by themselves, okay? So that's a favorable arrangement. That will happen, okay? This tends not to want to happen, okay, this anti-bonding thing up here, because it has a higher potential energy than either the two atoms have by themselves, okay? And so the way this works is basically you take your electrons from your atomic orbitals, and you just put them into the molecular orbital right here in the middle. Okay? Hydrogen only has 2 electrons, so those 2 electrons will both go into the bonding orbital. All right? And what that tells us is, and basically what you have to do here, is find the bond order of these 2 things, and it's half the difference between the number of bonding versus anti-bonding orbitals. So the example here, we have 2 bonding orbitals in this one. We have 0 non-bonding orbitals. So 2 minus 0, multiply that by a half, and you end up with a bond order of 1.
Brandon Heiser, if you're still in the building, please come to the registrar's office. Brandon Heiser to the registrar's office.
If the bond order is greater than 0, then the bond will actually form, okay? And so molecular orbital theory helps you to actually predict if 2 things will form a bond or not, okay? Now we know hydrogen forms a bond with another hydrogen, right? Because we know H2 exists. So this just kind of confirms it for us, all right? This has a bond order of 1. So H2 actually does form. That's a for real molecule. Thank you, molecular orbital theory, for telling us that, because we already knew that. But a good model will confirm what we know, all right? It fits the data, right? Okay, so let's think about helium, He2. Now, just based on what you know about helium, do you think that happens? Probably not, right? Okay, because what happens here, you take the 2 electrons from a helium atom, 2 electrons from another helium atom, so that's 4 total electrons we have to do something with, okay? Now again, I just want to kind of stress, I know this looks a little weird, but here's your orbital diagram for one of the heliums. Here's your orbital diagram for the other helium, and then this in the middle is the orbital diagram for the molecule if it would form, okay? And so then basically we put 2 of those electrons have to go in the 1s bonding orbital, the other 2 go in the 1s anti-bonding orbital, okay? So then if you take, 1/2 times 2 minus 2, well, 2 minus 2 is 0. Half of 0 is 0. Okay? Because this is 0 or less, the bond doesn't form. Okay? So that tells us He2 does not exist. Now here's where it gets a little weird. What about He2 1 plus? So let's think about this for a second. If we have a polyatomic ion, 2 heliums bonded, but they have 1 less electron than they're supposed to. Now, the bond order is 1/2 of 2 minus 1. The bond order is 0.5. In theory, could He2 plus form? When I say He2 plus, I mean this. Okay. In theory, yes, right? Guess what? This is really weird. They've actually been able to make that in laboratory settings. 2 heliums combined together with a positive charge. It's a polyatomic ion of helium. That's crazy, isn't it? Okay, so, but it fits with molecular orbital theory, okay? And the reason why is because we only have 1 of those anti-bonding electrons up here, okay? And so there's more bonding electrons than there are anti-bonding, and so you end up with a favorable arrangement, okay? All right, so when you have both s and p orbitals, it gets a little bit more complicated, okay? But basically, you're going to end up with s bonding orbitals, okay, and s bonding and anti-bonding, like we just talked about over here, okay? Those are the 1s bonding and anti-bonding. And then you can also have p bonding and anti-bonding, all right? And there are 3 different p orbitals, okay? So you end up with, again, 6 possibilities here, okay? So if you're looking at an orbital diagram for something with p orbitals, it's going to look more like this, okay? So you've got your s's down here, okay? So you've got your s bonding and then your s anti-bonding. Now the asterisk, by the way, that you might notice on these, I don't know if you can see it from where you are, those are the anti-bonding, okay? and then the ones without the asterisk are just the bonding orbitals. So you make a molecular orbital diagram for something, and it's going to end up looking like this. And basically, you can, for anything in the second row, you can just think about the number of electrons that it would have. So, I mean, something like nitrogen, okay? Just picking something. So nitrogen's, if we wanted to see if N2 would form, okay? If we want to see if that would be a favorable thing. I'm just keeping it really simple here. Nitrogen bonding with a nitrogen, okay? So this thing is really off center. Really, hang on, sorry, that's gonna bug me. Sorry, give me 1 second. I just guessed on that top one. Okay, see if that's better. So in a nitrogen, these are our 2s. The 2s, there we go, that is better. The 2s orbital's filled, right? And then with nitrogen, we've got half-filled p orbitals here, okay? Same thing over here. If we've got another nitrogen on this side, the 2s orbitals are filled, and we've got the half-filled p orbitals. Have I lost you yet?
No.
Oh, okay. All right. So then basically you just kind of fill this in based on the number of electrons that we have here, okay? So obviously here, this is going to be completely filled, the s bonding and anti-bonding, okay? And then you just kind of fill from the bottom up on this one, okay? So we've got 1, 2, 3, 4, 5, 6, okay? Is that how it fills? I need to double check that, because that doesn't seem to fit with Aufbau's principle, does it? Make sure I'm not teaching you something wrong here. I probably am. I usually do. I do have a problem with that. No, that's right. That's right. It's going to fill the bonding before it fills the anti-bonding. So I don't think I quite filled it right. I think what I should have done is filled it like this. 1, 2, 3, 4, 5, 6, like that. Okay. And then we're following Aufbau's principle, because these are much higher energy to be an anti-bonding. All right. But that gives you a pretty good idea that probably, because we've got a lot more bonding electrons here than we have anti-bonding electrons, that N2 is probably a stable molecule that would form. Does that make sense? Okay? And so that's kind of what you're looking at. What you would need to be able to do with these molecular orbitals is not to actually draw the diagrams, but you need to be able to look at a molecular orbital diagram and assess, would this bond actually form or would it not? Does that make sense? Okay, so what you actually have to do with it is not so bad. Now you just have to remember, you take the bonding electrons minus the anti-bonding, and then just multiply that by 1/2. That'll give you the bond order. If the bond order is greater than 0, then the bond will probably form. Okay? Now, the nice thing about molecular orbital theory, this stuff I'm not worried that you know. There ends up being an overlap in the second energy level. Not a big deal, okay? But if you look at how these things fill, if you look at something like oxygen, for example, okay? This would kind of suggest for oxygen that it's probably, that O2 is paramagnetic. Does that make sense? And the reason I say that is because of these unpaired electrons right here, right? That would probably make O2 paramagnetic. Now, if you look at the Lewis dot structure for O2, make sure I get this right. Doesn't look to me like there's any unpaired electrons there, does it? Looks like everything's paired up. And that's where the Lewis model kind of fails us, because if I was going to predict, just looking at the Lewis model, whether this thing was attracted to a magnetic field or not, I would probably say, no, it's not. It's probably diamagnetic. But if you look at the molecular orbital diagram, there's 2 unpaired electrons there, so yeah, actually it probably is attracted to a magnetic field. Turns out oxygen O2 is paramagnetic, okay? Now, what we've talked about with paramagnetic versus diamagnetic so far, we've talked about individual atoms being paramagnetic or diamagnetic. This is now talking about molecules, okay? So another thing that you would be able to probably need to do is look at an orbital diagram for a molecule and be able to predict, is it paramagnetic or diamagnetic? But that's super easy because all you're looking for there is, are there any unpaired electrons in this diagram, right? So again, this is kind of like sigma and pi bonding. It's complicated, but what you actually have to do with it is fairly easy, okay? So I don't think there's anything else I really need to say about the molecular orbital theory. But I just wanted to make sure that you guys kind of got a brief overview of that. I think there's a couple other things in the reading guide that you would probably want to look at. And tomorrow, I'm going to try to move a grape with a magnet using this concept. So we'll see if it works. I haven't tested it yet with that magnet. Yeah. If any magnet's going to move the grape, it's going to be that one, right? Okay. So anyway, that's it for today. Yeah, watch your fingers with that one.